Hello, everybody out there. Welcome to another multivariable calculus video. One day I promise I will be able to edit my hand out of these, but today is not that day. So bear with me as we talk multivariable limits. So when we're looking at multivariable limits, we have some function z is equal to a function of x and y. If we look at the limit of z as x and y go to some function, it's a lot like our old limits from 1D calculus, except rather than looking at what one of these guys, x or y, is doing, we're looking at what both of them are doing together. As we approach some, x and y, we call some special point x0, y0. So as x goes to some point x0, as y goes to some other point y0, what happens to my function f of x and y? It hopefully equals some value L that we call our limit. It's just now that we're in multivariable land, there's a lot more freedom to how we can get to x0, y0. There are many roads that lead to the same place, and kind of the big moral of this whole thing is they all need to lead to the same place. So we can approach x0 and y0 in any direction. A lot like doing 1D limits, if they're nice, it just really boils down to plugging in whatever values x0 and y0 are into your function and seeing what happens. So if I have the limit as x and y approach, we're going to have x go to 0, and we're going to have y go to 1, and our function is going to be x minus xy plus 3 over x squared times y plus 5xy minus y cubed. Now again, this function describes some surface, kind of like a wrinkled blanket of some sort in space. I couldn't even begin to tell you what it really looks like. Desmos it if you're interested. But the idea is we want x and y to approach the point 0, 1. So every time we see an x in this function, we're going to replace it with a 0. Every time we see a y, we're going to replace it with 1. And what we get is 0 minus 0 plus 3. All those x's nicely cancel out. They'll do so in the denominator as well. And then we get minus 1 cubed is just 1. So hey, this function is going to approach the value negative 3 along as measured on the z-axis or something like that, as x goes to 0 and y goes to 1. So we're looking at what these two variables are doing as they each go their own point, and we get some number out. Sometimes it doesn't always work so nicely. Maybe if I'm looking at the limit as x and y go to the origin 0, 0, as good a point as any to go, and we're looking at the function x squared minus xy over root x minus root y. Now, clearly, if I plug in 0 here, I get 0 on the top, 0 on the bottom. We get an indeterminate form. And there were lots of ways to tackle that in the past, and a lot of our ways to tackle that in the past are going to go now. We have the square root form here, so we're probably going to tackle this by multiplying top and bottom by the conjugate here. We have a root x minus root y. If we multiply the top and bottom by root x plus root y, maybe this will work out a little nicer. And so what we can do is multiply by that conjugate. Parentheses are your friend. We get root x minus root y times root x plus root y. If we work out that denominator, the cross terms go away, and we get an x squared minus y squared. Sorry, just x minus y, rather. Root x squared is just x. We can work out, maybe I'll leave it for now. So we've made the denominator a little better. It's still 0 minus 0 down there, but if I factor out an x from this first term here, I do get x minus y, and we have a nice removable whole So this factor down here cancels up with the factor up there. What we're left with is x times root x plus root y, which I just plug in 0 into everything and I get 0. So we were able to evaluate this limit by using a conjugate trick, which is an old Calc 1 thing. So no real surprises there. It's just now there's y. So that's the idea of limits. One thing we do need to be wary, though, is that we can approach in any direction. So if we define a new function, f, I'm going to define it piecewise, where we have 2xy over x squared plus x squared, y squared, when x and y are both not 0. And then at the origin, 0 at 0. So if we're away from the origin, the function looks like this. Clearly, if it were 0, it would blow up. So we allow the function to equal 0 and see if, maybe the function will approach it there, maybe it won't. We need x and y to approach the origin and reach the same value along any choice of path. If we think back to 1D calculus, if I had some function that was piecewise like this, and it's defined, I can approach one value coming from the right, I can approach one value coming from the left, and there will be different values there. That's okay. Those left and right limits both exist, but the actual limit at this point here does not exist because these two paths do not agree where they're going. The left one goes one place, the right one goes another, and the limit does not exist as a whole. The same idea goes for multivariable land, except now we can approach the origin. If we're looking at a bird's eye view of the xy plane, there are any number of paths we could come in at, and we want them all to reach the same z value for this to work as an actual limit. If any of them does not approach the same way as the other one, the limit can't exist. So they all need to agree. All the roads need to lead to Rome. A way we can test this is we kind of test a bunch of paths at once. So we choose y to equal mx. So the idea here is that we are, approaching the origin on a bunch of different lines. M is the steepness of those lines. If the limit exists, it doesn't matter how steep that slope is in the xy plane. I can proceed down that path and I should hopefully get the same value. So I can make this substitution. I'm going to let y equals m times x. And what I get is 2x times mx over x squared plus m squared y squared. Sorry, x squared. Y is mx. So when we square mx, we get m squared x squared. So I can factor out an x squared from the denominator. I get 2x squared m on top. I get x squared times 1 plus m squared. The x's cancel. And the fact that I had the x's cancel and not the m's means that the limit here is path dependent. It depends on how steeply I'm approaching that point. And so if I choose y equals x, m equals 1, I get a certain value. Let's try that. Y equals x. We get 2 over 2 equals 1. So maybe the limit's equal to 1. If I approach just along with a slope of 0 along the x-axis, y equals 0, that means m is equal to 0, and I get 0 over 1 is 0. And these don't match. So because any m I choose is going to get me a different value, the limit does not exist. We need this to have the same value regardless. So if the m's canceled and it was just a constant value, or if somehow I got like 2m over 2m and it was always equal to 1, then that would be fine. But the fact is, how steep I'm approaching the origin will change the value of z for this function. And so there's not any one limit. We can't agree upon the limit, and the limit does not exist. All right. So now that we've defined the limit, we could probably take a moment to say that, if I had a function of three variables, w, x, y, and z, we can extend this idea. It's just we need, what are x, y, and z all approaching? I can evaluate the function at that value. So maybe I have the function looking something like z times e to the negative 2y times cosine 2x, and I want to find the limit as x goes to pi, y goes to 0, and z goes to 3. Why not? So I'm going to plug in every x is going to become a pi, every y is going to become a 0, and all the z's are going to become 3's. So it's just, we're doing it more times now. There's another variable to consider. We need to see what happens as that third variable approaches that. And we can extend that to any number of variables that we cared to worry about. So just to, put a pinpoint in this one, we get 3 for z, e to the negative 2 times 0 is just 0. And then cosine of 2 pi. E to the 0 is 1, cosine 2 pi is 1, so the limit is 3. We did it. Now that we've introduced limits, we can use that idea to finally solve the mystery of what that weird curly D you keep seeing in places in your textbook is. And so now we move from multivariable limits to the partial derivative, one of the hallmark ideas of multivariable calculus, along with the multiple integral. This just extends the idea of derivatives and slopes and tangent lines to higher dimensions. The idea here is that we're taking a derivative with respect to one of the possible variables. Derive with respect to WRT one of the component variables. When I do that, the other variables, no matter how many other ones I have, they are all treated as constants. And I basically just, if I'm taking the derivative with respect to x, all the y's and z's are constants, and I just do what the derivative is with respect to that one variable. Everything else is a constant. So this is the easier one. It works out pretty nice. If we think about this as a limit, we're going to define a partial derivative as curly d with respect to curly dx. So this notation is one way to represent a partial derivative. We can think of it as, and we apply this to some function f, this is kind of like taking a regular derivative of x of our function with x as a variable, and then y is held fixed at some point. We want to know, if we want to evaluate this at some special point x0, we can consider this the limit of h going to 0 of our function x plus h times this fixed y0 subtracted from f0, x0, y0. So as h gets smaller and smaller, we're getting closer and closer to this point x0. But we're not doing anything to the y. Y is held fixed. We're only changing our path along the x direction. over h. And this looks like a lot like our normal definition of a limit. It's just that our function is defined for two or more variables, and we're only changing along one of them. So this would be like the rate of change in the I hat direction and the x direction. I can look at a similar definition, curly df, curly dy, and this is going to be the limit as h goes to 0 of our function x naught is now held fixed. That one's not going to change, but y is changing. Y is not plus h minus f of x0, y0 over h. And then we make h really, really small. We approach y0 closer and closer and closer and closer, and we get the rate of change in the j hat direction. And of course, you could do the same thing for if I had a three variable function, f of x, y, and z, I could look at the change along the z direction by, holding x and y constant and seeing how I change along that. Geometrically, we can think about it as, rather than having a function, a curve, we now have a surface. So again, here is our curved surface in space. There might be this curve here along that surface. And at some special point, x0, y0, you could draw a tangent line. But if I'm moving along the y direction, the tangent line is going to look one way. If I'm moving along the curve this other direction, maybe I'm keeping y fixed and I'm moving along the x direction, I get a different tangent line, which might have a different slope. So that's what our partial derivative is doing. It's telling us how steep this, function is at a certain point, depending on which way that I step. If I step along the y direction, I get one result. If I step in the other direction, it could be shallower, it could be steeper, but it's different. And so we have the x partial derivative and the y partial derivative to account for that. So how does this work? I have a function of x and y. Say x squared plus 3x plus y minus 1. And I want to evaluate it at the point 3, negative 2. I want to find both of its partial derivatives, df dx and df dy. Well, if I want to find df dx, I'm going to pretend like y is a constant. This might as well be 5 for all I care. And I'm going to take the derivative with respect to x. Anything that doesn't have an x in it at all, I basically ignore. And so now we just get 2x plus 3. We evaluate that at our point 3, negative 2. There's only x's in our result, so we plug in a 3 for x, and we get 6 plus 3 is 9. Then I look at df dy. I take the derivative. Now this x squared plus 3x, for all its rich structure, is a constant in y. So I take the derivative with respect to y. This negative 1 just was along for the ride, having a good time, but not really contributing anything. But the derivative's here. And we just get 1. That's it. So really for this function, if you're stepping along the y direction, no matter where you are, your slope is just 1. So that's kind of interesting. If our functions look a little more scary than a polynomial, there's no worry. We just, do the normal derivative rules, product rules, quotient rules, whatever, chain rule perhaps, but we are always treating the other variables as if they were constant. So now if I have f of x and y equals y squared times cosine xy, I want to find df dx. The x only lives in the argument of the cosine. So the y squared is just a coefficient out front. The y is just a constant multiplying our variable. So when we do this, we apply the derivative of cosine and the chain rule. So the chain rule is going to give us a minus y cubed. The minus comes from getting derivative is negative sine of xy, and then the extra factor of y comes from taking the coefficient of x and putting it on the outside. And we're done. If we do it for df dy, it's a little more complicated because now we have to do the product rule to take the fact that we have y squared multiplying this function cosine xy, and the chain rule will also apply again as we take the derivative of the cosine part. So we're going to do 2y cosine xy, derivative of the first times the function, plus the first function times the derivative of the second. We're going to get negative sine xy multiply by the derivative of the argument with respect to y. Instead of pulling a y out like we did over here, now we're going to pull out an x. And we can either tack that on the end or put it out front, wherever you want, as long as it's multiplying. So that is our partial derivative in terms with respect to y. A little more complicated, but it's just because when we do it with respect to y, we have a function of y multiplying the trig part, whereas for the x one, the x only lived on the trig part. Everything else was a constant. So that's what we have for that one. You can also derive multivariable functions implicitly. So perhaps if I want to find some derivative dz dx, but it's written in a way where I can't easily write it in terms of, z equals blah, 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 blah. For example, we have yz minus the log of z plus x plus y. I want to find dz dx. I'm going to take the derivative of both sides of this equation with respect to just x, knowing that z could possibly depend on x. Y, we're going to say, doesn't. And so when I do this, y is a constant, but z could depend on x. So I get y times dz dx minus derivative of ln z is going to be 1 over z. Chain rule pulls out an implicit dz dx. On the right-hand side, dx dx is just 1, dy dx is 0. It's a constant, so equals 1. I can now factor out the common dz dx from both of these terms here and get y minus 1 over z equals 1. And now I can find, hey, the derivative of z with respect to x is just 1 over that mess on the left-hand side, y minus 1 over z. So your implicit rules is still a thing you can do. It's just, again, anything that's not directly related to z or x is treated as a constant. Y is just, it could be a 3 for all we cared. Just like with one-dimensional derivatives, you can take derivatives multiple times. But the interesting thing now is that you can mix and match how you do that. So it turns out there's actually 4 second derivatives of a multivariable function in 2 variables at least. So I could look at df squared dx squared. And this would be I take the partial with respect to x, and then I take the partial with respect to x again. So this is 2 partials in x. Sometimes you'll see notation for this is just like f with 2 subscript x's. It's a little easier to write than writing the d's and the squares out over and over again. So whatever you like to do is up to you. I will probably interchange how I do it. So just buckle up for that. I could also do d squared f dy squared, which would be 2 partials in y. Or fyy. Ooh, but now I could start by taking a derivative of x, and then I do y. So this would be like partial x first, then partial in y. So we would write f x, y. I did x first and I did y next. Alternatively, I could do it the other way around. Maybe I do y first and I change of heart and decide I'm going to do x next. So this would be y first, x second. And of course, we would get f of y, x. So if we want to find second partials of a function, we have to find 4 different results. So let's try it with our friend here. F of x and y equals x cosine y, feeling cozy, plus y e to the x. Yikes, because it's going to be gross that we have to do it 4 times. So we can look at first. To do our second partials, we do have to take the first partial. So I guess we have to get really 6 results here. We get df dx first. So anything that's not x is just a constant. So the cosine y here, that's just a constant. So that's the constant we get. That's our coefficient of x plus y e to the x. Derivative of an exponential is itself. Y is a constant, so it stays. We can also get, I guess these are partials. I should curl these d's more. df dy. Now I actually take the derivative of the cosine part. I get minus x sine y plus, well, the e to the x is the coefficient of the linear variable y, so I just get plus e to the x. Now that I have these first partials, each one has 2 possibilities. I could double up on x, in which case this first term is 0, and I get df squared dx squared equals y e to the x. Or I could go with respect to y, do what we call a mixed partial. So we did x first, then y. We're going to get minus sine y plus e to the x, the coefficient of that y. If I do double y derivatives here, I'm going to get the e to the x part becomes 0. Negative sine y just becomes negative cosine y, so I get negative x cosine y is f y y. You can see I'm already getting lazy with my notation. I went to the other one. Or I could do y first, then x. So I'm taking the derivative of this with respect to x. I'm going to get negative sine y plus e to the x. Interesting. The 2 mixed partials, x first, then y, and then y first, then x, lo and behold, they are in fact the same thing. And yes, it's true. That will always be the case. These mixed partials, it is always true that fxy is equal to fyx. Mixed partials are equal. So yes, there are 4 things you might have to consider. We're going to be building matrices where, each element is a different one of these derivatives. But really, once you have one of these mixed partials, you have the other one automatically. So really, you get one for free. You only need to find 3 results, not actually 4. This is what we call Euler's theorem. He doesn't really name anything else in math. This is the only thing he has, and I'm just kidding. He actually names pretty much everything in math. This is just one result that he has. It says if f of x and y and its partials are defined, at the point where you're taking the derivative, then f of xy will equal f of yx. So that's a really powerful theorem. This is useful because sometimes it's easier to calculate it one way than the other. So if you can see that, hey, this one's going to get rid of a lot of things when I derive with x first, that can make your life a lot easier to get the same result. So for example, let's say we're looking at the function w equals x times y plus e to the y over y squared plus 1. If I'm looking at this, this is a lot of stuff in y. However, if I take the x partial first, this whole thing, as ugly as it may be, is just a constant. So if I take dw dx, first thing I get the coefficient of my x is just y, and then this whole beast is just a constant. It becomes 0 when I derive it. If I take two partials with respect to x, well now that is equal to 0. But the mixed partial, dw dx dy, is just 1, which means I also know that if I were to do it the other way around, I would also get 1. I'm going to go through the painstaking process of showing you that that's the case. I rarely care here at Docky's Talkies, so we're gonna do that, and we're gonna find the y partial dw dy. We get an x from our first term, and then we got to do quotient rule to do this next part. So we're gonna get plus e to the y squared plus 1 minus 2y times e to the y over y squared plus 1 all squared. Well, that looks pretty horrible. But when I take the derivative of this with respect to x, well, this is still all in just y. And so I didn't need to do all this. I could have just cut to the chase and did it the way we did it earlier. This part, when I take the derivative with respect to x, just becomes 1 again. So dw d y then dx squared equals 1, like we expected. I wanted to show you that this was the equality here, the mixed partials confirming Euler's theorem work for this function. I'm not going to find d squared w dy squared. You can do that as an exercise for the viewer. All right, and so that is the partial derivative. You're just really taking a complicated looking function and you're making it a lot easier, looking at how it only changes in one direction. And you can do that for any number of directions you have, and you should in principle get different results as the curve is steeper in one direction versus the other. All right, that'll do it. Thanks for joining us.